Okay, let me talk to you a little bit about the magic of water. We know it's H2O, 2 hydrogens with 1 oxygen, and you know the Bohr model. You're going to know what that looks like by now. And they're sharing electrons over here, sharing pairs of electrons. So that's a covalent bond. Both of those are. But it's going to turn out they don't share them equally. This is a polar covalent bond, which means uneven sharing of those pairs of electrons. The oxygen has more electrons, and so the electrons tend to stay closer to it. It draws more of those negative charges near there, and it's pulling the one that's around this hydrogen closer over there. The sharing is not equal. Oxygen gets more of those negatives. So as a result, we have a partial positive charge on the hydrogen side and a partial negative charge on the oxygen side of every one of those molecules. Then this little sign here that looks kind of like an S, that means partial. So partial negative here with the oxygen because it's got those electrons closer. Hydrogen, partial positive. And so this positive is attracted to that negative. And we end up with this wonderful map of this attraction, and that is what makes water so vital for life. And a little bit more of that, the partial negative and the partial positive. And so we end up with this whole map, like I said, where they're all connected with hydrogen bonds. Well, hydrogen bonds are pretty awesome, but there's something they do that nothing else does as well. They can work like a post-it adhesive. It'll stick where you want it and then come off when you don't want it to be attached. Why would that be important? Think of DNA. If you remember DNA, it's this double helix, and so it's a ladder that's twisted and twirled around, right? A twisted ladder, and these would be the steps of the ladder. So we've got 2 strands of DNA hooked together, and they're hooked together in the middle by hydrogen bonds. Why in the world? DNA is so important. Why would we want to be able to detach that? Why? To replicate it. We have to unzip it and then find new bases and hook them up. When we replicate a cell, we replicate the DNA. So I'm going to talk about the properties of water that make it act so wonderful. And these are the list of the 6 that we're going to talk about. First, it's a solvent. It used to be called the universal solvent, but not everything dissolves in it. Hydrophilic. Hydro, water, philic, love. City of Philadelphia, the city of love. So philic is to love. And that is going to dissolve in water. Example, salt. Here's some salt in there. There's your chlorine ion, there's your sodium ion, and they dissociate completely in water. And that means they dissolve in it. You don't see the salt crystals anymore. Hydrophobic means hydrophere. So that's not going to dissolve in water. Oh, here's hydrophilic again. And then hydrophobic. No charge, like oil and water, doesn't mix. So it doesn't have a charge. It's not polar, so it won't react with that polarity in that water molecule. Cohesion and adhesion. Cohesive, it sticks to itself. Adhesive, it sticks to other polar molecules. And an example is why, when you water a plant, it draws the water up. It's because it's evaporating, transpiring in the leaves. And so it's just kind of like sucking on a straw. And that's an example of cohesion and adhesion. The water sticks to itself as it's pulled up, and it sticks to the tree. High surface tension. It ends up having this coat of on the outside, almost like a skin, where those water molecules are more attracted to each other than they are to the air. And so certain things that are light enough can walk on it. And if you're clever enough, you can skip a rock. If you choose a flat one that you can throw just right so it doesn't break that surface very much. High surface tension. We use it all the time. This part is awesome. I'm not going to show you. You can watch it and decide if you think it's true or not, because I'm going to attach this in the class. I love it. It's well done. Let me come back. I'm already at 4.5 minutes, and I'll pick this back up again in the next one. Okay, I left you at liquid mountaineering, true or not. So I'm not going to talk about that because I really want you to watch it and see what you think. Then if you're not sure, look up like Mythbusters, liquid mountaineering, and see what they said. All right, So we're up to high heat capacity. That means water can absorb heat without a great change in temperature. So it makes areas more temperate that have a large body of water next to it. So that would mean areas of the world that are next to the ocean, but on a smaller scale, if you live next to a lake. I used to live on a lake in Oklahoma, and I could sail every afternoon because there was wind. Why was there wind? Because the water absorbed all that heat but didn't change temperature very much, while the air changed temperature really rapidly. So you had this difference in temperature between the water mass and the air mass, and then we have wind. Today in class, a student did a demonstration where she actually, it's kind of long and involved, but she ended up with these bubbles of gas in her hands, and she actually put her hand in water first, then in the bubbles of gas, and lit it on fire, and it didn't burn her hand. It was pretty crazy because water absorbed that heat energy. Her hands were cold. Don't try this at home, for sure, but it was pretty cool. And it was this concept that she used. She talked about it at the end. It was like boiling water in a paper cup. When you put a paper cup in coals from a fire, say, like if you're camping, it's going to boil because the water is going to absorb all of that energy and change temperature, but it won't catch the cup on fire because the water's absorbing all that heat energy. It's pretty cool. Watch that one too while you're watching them. High heat of vaporization. If you're older, you know where this came from. This came from a movie called Airplanes, this picture. But what's happening when you sweat is it's cooling you off. You may have known that. Well, what's happening at a molecular level is the water's come out of your body, you sweat that water out, it's a water molecule, and it takes energy to break those hydrogen bonds so it becomes a vapor and evaporates. And where does it take that energy from? From your core body temperature, so it cools you down. That's called high heat of vaporization. It takes a lot of energy to break those bonds. And it's one of the few things that is less dense when in solid form, when it's ice. What actually happens with those hydrogen bonds, they expand slightly. If you've ever put a Coke bottle in the freezer, sealed up, and forgotten about it, you were going to cool it down and forgot, it'll expand and blow out the end of the jar, whatever it was in probably. That's because ice was expanding because of those hydrogen bonds. Why is that important to life on Earth? Well, if you think of a body of water, that ice on the surface forms a layer of insulation. So all the organisms living underneath there do slow their body down. They have low metabolism because it's so cold, but they don't freeze solid because of that layer of insulation. And how does this relate to our roads? What happens? What makes a pothole? Water gets in these cracks, freezes, expands, makes the crack bigger, and we end up with potholes. So engineers do this really cool thing, like on the sidewalks. Do you see all those divisions that they've made right here and here? These small gaps, so the water can go in there and freeze and expand and not break the concrete. All right, magic of water, all done.